Topic: Moment of inertia. Moment of inertia is body's tendency to resist angular acceleration, which is the sum of products of mass of each particle in the body with the square of its distance from the axis of rotation, as shown in this slide. The distance between the center of mass and rotational axis is shown in these two hammers, that is denoted by R. Moment of inertia as a geometrical property of an area. Let us assume we have a wooden plank that we would like to use for crossing a canal. We can place the plank in two ways. One is the flat and one is the with shorter area of cross section. Now we can tell that here the plank will be stiffer if we put a load on the shorter side of the cross section. Some cross sections are much more efficient at resisting bending than the other ones, like the one with bigger or larger cross sectional area. The cross section on the right or that has less shorter cross section has more material located far from the bending axis, and so is this concept of resistance to bending can be quantified by calculating the area moment of inertia, which is also called the second moment of area. The area moment of inertia reflects how the area of cross section is distributed relative to a particular axis, and so is a measure of how much resistance the cross section has to bending. Now we will calculate the area moment of inertia. How it can be calculated for an arbitrary cross section like the one shown here? The first thing to note is that the area moment of inertia is not a unique property of a cross section. It quantifies the resistance to bending about a particular axis, and so its value changes depending on where we place this reference axis. We can approximate the area moment of inertia of a cross section by splitting it into small elements. Each element contributes to the total area moment of inertia by a quantity equal to its area dA multiplied by y square, where y is the distance to the reference axis, which is the x-axis in this case. We can sum up the values for all the small elements to obtain the area moment of inertia. For the entire cross section, it is denoted by letter I, and because the x-axis is our reference axis, we will give it subscript xx. We can define the area moment of inertia more precisely using integration as shown on the slide. If the y-axis is our reference axis, we can calculate y in same way. The parallel axis theorem. What do we do if we need to obtain an area moment of inertia equation for an axis that is not centroidal axis, but it is too difficult to calculate using integration? Fortunately, there is a method we can use to calculate an adjusted area moment of inertia for an axis that is parallel to centroidal axis. The adjusted area moment of inertia Ix dash x dash can be calculated by summing the moment of inertia of the centroidal axis and the product of the cross-sectional area A and the square of distance d between both axes, with Ix dash x dash is equals to summation of dA in bracket d plus y whole bracket square. That is Ix dash x dash equals to Ixx plus AD square. This is called parallel axis theorem equation, and this is the parallel axis theorem. Perpendicular axis theorem. We can calculate the third area moment of inertia for a reference axis that is perpendicular to the plane of cross section. This quantity is called polar moment of inertia, and it is usually denoted using the letter I. It represents the resistance of cross section to twisting about reference axis. It is calculated in the same ways as Ixx and Iyy, but using the distance to the axis rather than perpendicular distance to the x and y axis. So equation becomes Izz equals to Ixx plus Iyy. According to second moment of area, Ixx equals to summation of dAy square, Iyy equals to summation of dAx square, and Izz equals to summation of dA dot r square. Izz equals to Ixx plus Iyy, since r square equals to x square plus y square. This is the perpendicular axis theorem. This slide shows the different moment of inertia of different shapes. Thank you.